I really want to check that this works.
Yeah, I'm letting everyone in.
Okay, cool. It's what's going on with this thing?
Hello, everybody. I'm going to mute everybody as we enter. We're just quickly busy trying to get.
Okay.
Okay, just wait. There we go. All right. This is very funny. Chris is. Oh, there you are. Okay, your laptop is in. Hello, everybody. We're just quickly getting the technical stuff sorted.
Am I the host yet? Because screen sharing is still disabled.
Okay, it's coming now. Sorry, Chris, you're in. Your computer is in, but it says it isn't. It'll give us a second. There we go. Now you're in. I've just got to find you.
Okay.
Okay, there we go. Okay. All good?
I'll let you know now. Come on.
All right. Hello, everybody. Please come in so long. We're just busy sorting out the technical details of different hosts. And I think it works.
All right. Let me see. Sorry, guys. I'm still very much learning my way around this whole program. I'm trying something a little bit new today, which is working, instead of using my stylus to write everything out, I've already pre-made a couple of notes. And it'll also help you because right now I'm still learning how to write on this tablet without it looking like a child's writing. So yeah, everybody, please bear with me. Can you all see the notes I've put up here? I'm sorry if it is a little blurry. I've been having some real issues with my phone camera. Thumbs up, anyone? Can you see? Hello? Hello? Sorry, guys. Am I talking to anyone now?
You can see. I think everyone's still here.
Okay, cool. So, guys, the lesson that we're doing today. Oh, sorry. First of all, I'm Chris. Lovely to sort of meet all of you. The lesson we're going to be doing today is a very basic introduction to calculus, what it is, and a particular type of question that shows up in pretty much every single maths paper. So, as Diane told you the other night, calculus is one of the biggest sections in the maths paper, and it's really one that you will benefit from preparing well for. So, without too much ado, let's begin then. So, as I've got on the notes here, as it tells you, calculus is the branch of maths that deals with change, right? So, whenever we're looking at, I don't know, in the real world at least, rather, it's got endless applications. A lot of the time, we'll be looking at physical processes where we don't just want to know where something is at a particular point in time, or what the value is at a particular point in time. We need to know how it's changing. So that's all of the work that we kind of deal with in calculus. In practice, and particularly in grade 12 at least, calculus is all about gradients, right? And quick revision, as you can see here. Let's test this quickly. All right, so calculus, branch of maths, deal with change. As you guys certainly remember, I'm sure, your gradient is given by this formula here. M gradient is equal to y2 minus y1 over x2 minus x1. Or, as I prefer to think of it, your vertical change, your rise, divided by horizontal change, run. Right? And most important thing when you're doing these is to ensure that x2 and y2 and x1 and y1 come from the same points. Right. So that's our formula for average gradient. Now, the example that I use when I'm teaching calculus is usually the height of an aeroplane above the ground. Right? So, I've used the wrong piece of paper here. Let's say that we've got an aeroplane that has, well, we know that the height of the aeroplane is always, well, h, which is a function of t, is equal to t squared plus 2t, right? So that's the height of the airplane in hundreds of meters above the ground is a function of time, where time is the number of minutes since it's taken off. Well, to get 2 points, we'll say, all right, when the height when the time is 1 minute will be 1 squared plus 2 times 1 means that we're going to get 3. So the point will be 1 and 3. No, go away. Sorry. And then we say, all right, well, when the height is 3, sorry, when the time is 3, the height will be 3 squared is 9 plus 2 times 3 is 6, gives us 15. So our point 3 and 15 is also on the graph. So if we're looking for our average gradient, well, we'll say m is equal to y2 is 15 minus y1 is 3 divided by x2 is 3 minus x1 is 1. We get that our average gradient will be 12 over 2 is 6 units. Okay, now I'm pretty sure you guys are all comfortable with that idea of gradient, so we're not going to spend too much time on it now. But one thing that's important to know is that this only tells us the average rate of change in this airplane's height between when the time is 1 minute and the time is 3 minutes. And that's useful, but for pretty much everything important, we really need to know the rate of change at particular points in time, right? We're not just looking, what's going on? Sorry. We're not just looking at the average rates of change. We often want to know exactly what the rate of change is now. So when we're doing that, we're looking for what we call the instantaneous rate of change. 2 seconds. Sorry, guys. As I say, I'm really learning this on the go. Oh, man. I'm going to need to find a smoother way of doing this. Images. All right. Is that? Oh, I hope this is the right one. No, go back. That's the wrong one. Sorry, guys. I promise I'll be much smoother in the future. Come on, tablet. Stop sharing. I'll share. And here we go. All right. So when we're looking for the instantaneous gradient, the instantaneous rate of change, or the instantaneous gradient, we're looking for essentially the gradient exactly at a particular point, right? So one of the problems we would have if we're looking at a single individual point is just that using our normal gradient formula, gradient is y2 minus y1 over x2 minus x1. Oh man, it's not registering my stylus. The problem we've got is that x2 minus x1, if we're using an individual point, will be 0. Guys, sorry, I've skipped ahead just a tiny bit here. When we're looking at things like, the height of an airplane above the ground, or rates of flow of water into tanks, any kind of process in the real world, we usually want to know the rate of change at a particular point in time. So for instance, we would want to know what is the rate at which the airplane's height is increasing, at, say, when time is 2 or something like that. And we use calculus to find that. And we call that instantaneous rate of change the derivative. Now, in a curve like this one here, f of x is x squared plus 2x, you can see that the gradient of the curve is not the same at every point. At different values of x, you're getting different gradients, right? The slope is much shallower here than it is here. And because of that, we're not just going to get a single value for gradients. We're going to get a formula, right? And we call that formula the derivative. You put in an x into your f of x formula, and it gives you the y value, right? The derivative is a formula where you put in an x value, and instead of telling you the value of y at the point, it will tell you the gradient of the curve. And that's very, very important for a whole bunch of reasons, which you'll certainly get into later on in the section. So what we're looking at today, particularly, is a method for finding the derivative, which we call derivation from first principles, right? It's a bit tricky and a bit confusing at times, but in pretty much every single paper, or every calculus section paper one, you will be getting one of these. So if you can prepare yourself well, it's really marks in the bag that you can take into the exam with you. Because as long as you follow the rules and use the method properly, you should never lose marks on a first principles derivation. So now that we've gone through a bit of that, let's actually look at what that involves. Let's just go back a bit. All right, where is my eraser? Great. So let's consider this function that we have here, where f of x is equal to x squared plus 2x. And let's say what we want to know is we want to know the slope of that curve exactly at the point where x is x, right? Bear with me, it's a kind of a theoretical thing. Well, we obviously can't just use our normal gradient formula, m is equal to y2 minus y1 over x2 minus x1, because when we're looking at a single point, the x values and y values are the same. And so this formula doesn't really give us any easy way to assess the slope of the curve at a particular point. But using these first principles, we can do it. And the way we think of it is we conceive of a second point on this graph, right? As you guys, I'm sure, are familiar, y and f of x are the same thing. So if I've got this graph here, my first point here has an x value of x and a y value of f of x, all right? And what we're going to do is we're going to consider another point on the graph here where we increase our x value by an amount that we just call h. So if my x value there is x, this will be my x value. Well, this point here will be x plus h. So yeah, x plus h. Sorry, get up. Whoa. Oh, sorry, back to this. That'll be my point f, well, x plus h, and my y value will be f of x plus h. Again, so the way I think of it now is a lot like the way that I would think of a normal gradient problem. So I could say that my gradient, or in this case, my derivative, which I call f dash x, would be equal to, well, my y value at point 2, which is f of x plus h, minus my y value at my first point, which is f of x, all divided by, well, my x value here would be x plus h, and my x value, first point, is just x. And so what we end up with here would be f of x plus h minus f of x. And at the bottom, I'm just left with h. Now, the real problem that we've got is that ultimately we're not looking to get an average gradient between 2 points. We're looking to get the gradient at exactly this point, where x is x. And the way that we do that is we consider that if we were to, instead of just this h, if we were using an h that was half as big, would you guys agree that the average gradient between those 2 points would be much closer to the real instantaneous gradient than the average was with the larger h, right? As our value of h gets smaller and smaller and smaller, the average gradient between those 2 points gets closer and closer and closer to the real value of the instantaneous gradient. And guys, it might be a little confusing now, but it'll definitely make sense to you in future, that the real instantaneous gradient is always equal to the gradient of the tangent to the curve at that point. All right, if you're feeling lost, I understand completely. I'm now going to show you how we would practically do that in this example here for the formula f of x is x squared plus 2x. So, no, go back to Zoom. All right, on to Whiteboard here. So, I know that my original formula here is that, well, y, which is the same thing as f of x, is equal to x squared plus 2x. All right? So, when I'm using first principles, I'll say that my derivative, f dash x, is the limit as h tends to naught of my formula f of x plus h minus f of x divided by h. All right? And the reason I say my limit as h tends to naught is because I can never actually make h 0. But the smaller h gets and the closer to 0 it becomes, the closer I get to my real value here. So f of x plus h, what I need to do is take this original formula, and everywhere I have an x, I need to replace it with an x plus h. So f of x plus h is equal to, well, x plus h replaces x, so x plus h squared, plus 2 times x plus h. So that'll be x squared plus 2xh plus h squared plus 2x plus 2h. And my f of x, as always, is just x squared plus 2x. So putting all of that into my derivative formula, I get that my derivative is the limit as h tends to naught of, well, f of x plus h is x squared plus 2xh plus h squared plus 2x plus 2h. Sorry. Yo, guys, sorry. I mean, just very new to you working with the stylus on this pad. I'm just trying to think of how best to do this here. I'm going to turn it around. All right. Sorry, bear with me a moment. Clear. Oh, yes, a new one. Sorry. All right. So I've got f dash x is equal to the limit as h tends to 0 of. So my f of x plus h was 2 man. My apologies, guys. I really am struggling with this tablet today. It's all a big learning curve for me. So my f of x plus h is x plus h squared plus 2 x, whoa. Sorry, I think I understand the problem. It doesn't seem to be picking things up at the top. So, my derivative is my limit as h tends to 0 of x plus h squared plus 2x plus h. That there is my f of x plus h. It's the exact same thing as f of x, replacing every x with an x plus h, minus my f of x, which will be x squared plus 2x all over h. Now, when I square all this out, I'll get x squared plus 2xh plus h squared plus 2x plus 2h from multiplying out there, minus x squared minus 2x divided by h. Now, guys, one key thing that you should always know about these first principles is that when you do this up here, every term in this top line here that does not contain an h should cancel out. And if it doesn't, that means you've made a mistake. So over here, I have, well, x squared and a minus x squared. Those two cancel each other out. Again here, I've got plus 2x and minus 2x, which also cancel each other out, right? And what that leaves me with at the top is always going to be some kind of, well, some sort of, what would the word be, an expression where every single term contains h. So I've got, again, sorry, never forget to write your limit as h tends to 0, even if you have to add it as an afterthought. So it's the limit as h tends to 0 of 2xh plus h squared plus 2h, all divided by h. Now, when I say limit as h tends to 0, what I really mean is that ultimately I would like to put 0 in for h, right? Because that would give me the average gradient between f of x and f of x, well, between x and x plus 0. So what I really want to do here is get rid of my h's by taking out a common factor on my top line and cancelling it with the h in my denominator. So taking out a common h here, I'll get 2x plus h plus 2 divided by h, and again, the limit as h tends to 0 of that. Well, having taken out the common factor h, I cancel the top one with the bottom one, and what I'm left with is 2x plus h plus 2, my limit as h tends to 0. Well, as I said, what we're always really keen to do is to get, well, to put h as 0 in. So, sorry, just going back here. Once I'm there, let's just, well, go across to here. I can now stop writing the limit as h tends to 0 and just put 0 into this equation to get my final answer. And the final answer tells me that my derivative f dash x, if I put 0 in here, will just be 2x plus 0 plus 2, or just 2x plus 2. Okay. Now, that might have been a little confusing for some of you, so let me quickly just give you another example. let's say we're looking at a function like f of x is equal to 3x squared plus 1. All right? Well, actually, let's just make it 3x squared. Let's keep it simple. All right? I'm looking to find my derivative. In order to do that, I'm going to use my first principles formula. F dash x is equal to f of x plus h minus f of x. I keep forgetting it. The limit of h tends to 0, all divided by h. Okay, so again, to find my f of x plus h, I take the formula, and everywhere that I have an x, I substitute x plus h. So for this formula, f of x plus h will be 3 times x plus h squared. And my f of x will just remain as 3x squared. So my derivative from first principles will say f dash x is equal to the limit as h tends to 0 of, well, this will be 3. And x plus h squared gives me x squared, sorry, plus 2xh plus h squared minus f of x, which is just 3x squared, all divided by h. Then I multiply my 3 across the top here and get rid of all my brackets. So it's equal to the limit as h tends to 0 of 3x squared plus 6xh plus 3h squared minus 3x squared. And all of that divided by h. Again, once we reach this point where everything's multiplied out and simplified, you should be able to cancel out every single term on this top line that does not contain h. So you see we got 3x squared, 2 terms with h, and then minus 3x squared. That 3x squared and that minus 3x squared cancel each other out. And we're now left with a numerator that has h in every term. So again, I take out my common factor of h. It's the limit as h tends to 0 of, well, common factor h leaves me with 6x plus 3h, all divided by h. I cancel those two, and now I can stop thinking of this as being the limit as h tends to 0 and actually plug 0 in, because I no longer have 0 as my denominator. So we no longer write limit of h as h tends to 0, and now that just makes it 6x plus 3 times 0 is just equal to 6x. Okay. Guys, can I quickly just ask if anyone has any questions? Raise your hand now. Nobody? Okay, cool. So, as I said, the first principles is something that will come up every single exam. It's usually worth at least 4 or 5 marks. A lot of the time, they'll try and make it a little bit more complicated for you, right? So, for instance, let's say we've got something like f of x is equal to 3x squared plus 6x, right? The most important thing to remember with these is that whenever you're doing it, you need to replace every x in the formula with an x plus h. If you forget to change this, well, this particular x here into x plus h, that's probably the most common mistake that leads people off track in first principles questions. So we'll say the derivative of x is equal to the limit as h tends to 0 of f of x plus h, which here will be 3x plus h squared plus 6 times x plus h minus f of x, 3x squared plus 6x, all divided by h. Again, we're going to square out and multiply everything through, and then gather all our like terms, hopefully into an expression where everything that doesn't have an h will cancel. So the limit as h tends to 0 of 3 times x squared plus 2xh plus h squared plus 6x plus 6h minus 3x squared minus 6x. Multiplying through here, the limit as h tends to 0 of 3x squared plus 6xh plus 3h squared plus 6x plus 6h minus 3x squared minus 6x. Again, you'll see that the terms we're getting from our f of x will cancel with all of the terms from our f of x plus h that don't contain an h. So I've got 3x squared, which cancels with minus 3x squared. I've got minus 6x, which cancels with plus 6x. And you can see that every term remaining contains h. So all of that divided by h. Now I take out my common factor of h, and I'm left with 6x plus 3h plus 6h. Yes, sorry. Hang on a second. Oh yes, sorry. This h has been taken out as a common factor. All divided by h. Cancel those. Now I can stop writing limit as h tends to 0 and put 0 in for all of my h's, and I'm left with 6x plus 6. Right. Guys, any questions on that? All right. So I'm thinking we should now do a slightly more complicated example. Is everybody clear on the basics or the basic principles of what it is that we're doing here?
Yeah.
Okay. So I want you all now to quickly, does everybody have pen and paper there? Well, if you do, I want you to try. I want you all to try and find the derivative of, from first principles, of a function that is f of x is equal to 2x squared. All right, I'm going to give you 1 minute to try and get ahead here before I start going through. Well, before I start going through the answer. Remember, to find my formula, well, to find my expression for f of x plus h, I simply replace every x with an x plus h. All right, so hopefully you've all gotten ahead of it. And we got that our derivative, f dash x, is equal to, well, f of x plus h will be 2x plus h squared minus our f of x, which is just 2x squared divided by h, and the limit as h tends to 0. Well, squaring out now, we're going to get that's 2 times x squared plus 2xh plus h squared minus 2x squared, all divided by h. So that'll give me 2x squared plus 4xh plus 2h squared minus 2x squared limit as h tends to 0. If you've done it correctly, you should find that 2x squared we cancel with minus 2x squared, and I'm left with an expression on my numerator that has x in, that has h in every term. So I'm going to take h out as a common factor, and I'll be left with 4x plus 2h. Now I've cancelled my 2 h's, and I can stop writing limit as h tends to 0. And that tells me that my derivative, f dash x, is equal to 4x. What's the time here? All right. Guys, is everybody with me up to there?
Yes.
All right, cool. Now, quite often the questions that you'll get in your exams will be, come on, tablet. No. Get out of, sorry guys. This really is a learning curve for me. Share, whiteboard. Okay. So one of the more popular ones that you'll get is you'd get something where they'd ask you to find the derivative of a formula like f of x is equal to 1 over x. Right? Now, this is a particularly daunting one, or it can seem like it, but if you follow the same steps at each stage of it, the same method will get you the correct answer. So if f of x is equal to 1 over x, my f of x plus h will be equal to 1 over x plus h. And then I'll use the same steps. Say that my derivative, f dash x, is equal to f of x plus h x plus h minus f of x divided by h, limit is h tends to 0. Now, I think like everybody, I hate working with triple stack fractions, so going forward, I'm going to turn that into the limit of, the limit as h tends to 0 of 1 over x plus h minus 1 over x times by 1 over h. And the method really is exactly the same. I need to bring these two together and make sure that I'm able to take out common h to cancel with the 1 over h over here. So I'm adding, well, subtracting two fractions that have different denominators, and my lowest common denominator here will be x times x plus h, right? On the top of this one, I'll now have x, and the top of this one will be x plus h. And I've now brought these two together with the lowest common denominator times 1 over h. Oh man, keep forgetting it. But remember, you can always add it later. Just make sure that it's actually there. So then, that gives me, well, it'll be the limit as h tends to 0. At the top here, I'm now going to have x minus h divided by x times x plus h, all multiplied by 1 over h. So here I get x minus x falls away, and I'm left with this being the limit as h tends to 0. Sorry, shouldn't have put that line there. It's just the limit. The limit as h tends to 0 of negative h over x times x plus h, well, multiplied by 1 over h. Sorry, that's one single bracket. Well, here I can easily see that I've just got, well, h here will cancel with the h here, and I can now substitute 0 in for h, and I'm left with 1 over x times x plus 0, which is equal to 1 over x squared. All right. Now, luckily for us, there are ways of getting derivatives that don't rely on first principles. And those are the techniques that Diane was going through with you guys earlier this week. In general, I can say that if I've got f of x equal to ax to the p, then my derivative of x will be, well, I bring my exponent here down, multiply it on the front, so it'll be p times a, and then I subtract 1 from my old exponent. So a way of thinking of that, well, sorry, not a way of thinking of that, just an example of that, would be that if my f of x is equal to x to the 4, then my derivative, f dash x or f prime, depending what you decide to call it, is equal to, well, I bring 4 down to the front, multiplied by the 1 that's here, and then my exponent was 4, subtract 1, so it'll be 4x to the power 3. Or another example, if I've got f of x equal to 1 over x, well, as you guys know, if I've got 1 over x, that's also equal to x to the power negative 1. So if I'm taking a derivative of 1 over x, well, then my f prime of x will be equal to, well, this negative 1, I'm going to bring down to the front, so it'll be negative x. And then my old exponent was minus 1. Minus 1 will give me a minus 2, which is the same as 1 over x squared, which was our answer in previous slide. Yeah. So as you can see, the two answers that you get from those methods are the same. I apologize for this having been a bit of a shaky lesson. I'm really still learning how to use this tablet stylus thing. It's making me feel quite incompetent at the moment. But I do hope that you guys have all got at least some idea now of what calculus is and how the first principles questions work. Guys, does anybody have any questions?
No.
Nobody? Nothing?
Nope.
All right. So guys, that being the case then, I think we can call it. We are 45 minutes done. I'm going to be practicing this a lot, and in future, I really do hope to have much, much smoother and less shaky lessons with you all.
Thank you.
All right. Thank you very much.